All right, good afternoon, everybody. Sorry it took so long to get this one posted. You can continue to use the previous video that I posted from last year. This gives you just a little bit more information as well as a couple more practice problems to sort of run through. We're going to take our time in section 2.3 and we're going to look at the mole. That's going to be what is the mole, how to convert using the mole, those types of ideas, which are going to be very helpful as we continue on through this unit. Now, our biggest idea here is that we want to see how we can actually use this mole, this whatever it is, to examine how the amounts of different things will affect chemical reactions. And this is all setting us up for stoichiometry, which is coming just a couple videos down the line. Now, what is the mole? The mole is a counting unit. Basically, like we said, a dozen or a pair, a gross, these are all things that when we say them, we should know exactly the value that is there. In the same way, we needed a way to figure out how to count particles or atoms or molecules, all these different things. And so, through much experimentation, looking at the Millikan oil drop and a lot of research by Avogadro, we come up with this actual value. Now, this is an actual counted value, so I don't think this is just something we made up. Now, this stands for 602 billion trillion. Now, to give you a little bit of perspective on this, this is a real number. But one of the examples I believe we're looking at is that if we had, skip it, we'll come back to that. Now, in scientific notation, 6.02 times 10 to the 23rd is how we're writing. This makes it much easier, and plus we don't have to write some of these zeros in order to get it. Now, this is named in honor of Mr. Amadeo Avogadro. We're going to talk about him a lot throughout this year. We talk about gases especially. We're going to talk about his different postulates. Now, a mole contains 6.02 times 10 to the 23rd particles. No matter what it is, if I have a mole of cars, a mole of cookies, a mole of animals, whatever it is, it's always going to be the same number. Now, one of the reasons why I wanted to make sure this is clear when I say the word particles, right here, particles can be individual atoms, it can be molecules, or it can be formula units. Now, you notice here I made this little note that says that that ionic compounds don't necessarily form molecules. Now, the reason behind this is they don't actually form a bond. They're just attracted, and we need to talk about that when we get to Coulomb's attractive forces. So, when we look at an ionic compound, what we're really saying is, especially in the case of what we have for sodium chloride, we have 6.02 times 10 to the 23rd sodium ions, as well as 6.02 times 10 to the 23rd chloride ions. Now, depending on the formula, we can, of course, adjust this. But we want to look at overall, the biggest thing we're looking at. If I have a mole of any of these things that count as particles, again, that's atoms, molecules, or formula units, all of those will count as a part of this 6.02 times 10 to the 23rd. So make sure you're paying attention as we go through the practice problems. Pay attention to which form it is that you're going to be dealing with. Now, molar mass. We spent a little bit of time and we're talking about how we developed the mass on our periodic table. We found out it's the average atomic mass, or the average of the different isotopes that are put together. Now, when I take a regular sample, all of those different isotopes may be included. So my mass is going to be, it's going to contain the cooperative or the amount by mass according to what's on the periodic table. We're going to use that number to then represent our mass in grams, or what's called our molar mass of that compound. Now, easy way to do it is equal to the average atomic mass. So directly from your periodic table, no guesswork on that part. Now, so that means if I'm using 1 mole of carbon atoms, that means that they would have a mass of 12.01 grams. Or 1 mole of magnesium, 24.3 grams. 1 mole of copper, 63.55 grams. Taking this directly, and I guess the basic idea is this allows us to move from a micro, very, very small, to a very macro, a very large view, something we can actually work with and do reactions with, and that is our goal. Now, when you hear molar mass, if I say molar mass of a particular molecule, molar mass of a particular formula, we're still looking at the same information. So we're still looking at the information we got from our periodic table, but now we are looking at it in terms of the entire compound, not just a single part. So even when you hear all of these terms, they mean the same thing. So make sure you have that clear. Now, how do we find the molar mass of a compound? Well, a simple way that I do it, and some may choose not to, but I like to make a little table. It makes things much clearer and much easier for me. First thing that I'm going to figure out is I really need to figure out what are my elements that I'm dealing with here. In the case of my example here, oops, missed it. We're actually dealing with copper chloride. Let me go ahead and put this at the bottom here. We're actually dealing with calcium, chloride. Now, in that compound, I have 1 mole of calcium, 2 moles of chloride or chlorine ions. So, with that being the case, I'm just going to go to my periodic table and find my masses. 40.08 for my calcium, 35.45 for my chlorine. Now, since I have more than 1 mole of my chlorine, I have to multiply it by the number of moles I have. I have 2, so I'm going to multiply the 35.45 times 2. This gives me a mass that I'm dealing with here of 70.90. So 40.808, plus 70.90 gives me a total of 110.98 grams. This would be considered my molar mass for calcium chloride. If I have 1 mole of calcium chloride, this is the value that I'm going to use. We're going to see how this is going to play out into our next section, which is our conversions, using the same information now to find out even more information. Now, when we do any type of calculations and we convert between grams and moles, what we're actually going to use is our molar mass. This is why it's so key. That you understand how to go ahead and compute the molar mass, as well as to making sure you're going in the correct steps. Now, if we're using the example of what we have here, converting between moles and grams, we have this question. Aluminum is often used in the structure of lightweight frames. Now, how many grams of aluminum are there in 3.00 moles of aluminum? So what we're trying to find is, we're at 3 moles of aluminum, and we're trying to find out how many grams of aluminum that is. So what we have to do is we have to set it up in our lovely, lovely chart. Now, remember that we want to place our unit that we want to get rid of on the bottom. So the unit that we're given here is moles, so that means moles also has to be on the bottom here. So we'll be able to cancel it out. 1, gone. Now, our molar mass we took directly from our periodic table. The mass of aluminum is 26.98 grams. So, in the long run, all I end up doing is 3 multiplied by 26.98 divided by 1, which gives me the same value, will give me a total of 80.94 grams of aluminum. Within this one question, based on setting up my information, taking my given piece of information, and the fact that I know that I'm looking for aluminum, and the question asked me how many grams, this let me know that I was going to need my molar mass. In using my molar mass, I'm able to find out exactly how many grams are present. Now, the same rules are going to basically apply. We talked about the 6.02 times 10 to the 23rd. They're basically still going to apply as we deal with particles. And I know some of this is moving kind of quick, so don't worry. I'll have plenty of examples that we can work through in class. Make sure you write down your questions up. Now, using the conversion factor that we've set up here, knowing that 1 mole equals, 6.02 times 10 to the 23rd particles. Again, that can be molecules, can be atoms, can be formula units. Being that we know that relationship, we can now use that to figure out information such as how many molecules are present in 0.25 moles of carbon dioxide. So, setting up my table just as before, my 0.25 moles of carbon dioxide are given to me in the problem, and my goal is to figure out how many molecules. So, this is where I got to go into it. So, I have my 0.25, my given, is still written in the same place. And since I want to get rid of moles of carbon dioxide, I'm going to make sure it comes to the bottom, so I'll be able to cancel it right out. Now, since 1 mole goes to the bottom, 6.02 times 10 to the 23rd molecules is on the top. And now it's just a matter of plugging it into my calculator. Now, depending on your calculator, we want to pay attention to a couple of different things and how we're actually going to put this in. You don't want to punch into your calculator the 6.02 and then hit the times button, 10, and then caret 23rd. That will not give you the correct value. This is wrong. Do not do it. What you want to find, especially if you have either the graphing calculator, TI graphing calculator, or if you have the TI 30XA, the ones we use a lot in class, what you're going to actually do is hit 6.02. Then you're going to find the EE key. It looks like two capital E's put right together. Then it's going to give you a little box, and then you're going to put 23 right in that box. This is what you want to do when you're putting in scientific notation. Do not do this. This will only lead you to a wrong answer, so I want you to be very careful of that. Now, after we've gone through and calculated, plug this into our calculator, 0.25 times 6.02 times 10 to the 23rd power. We're going to end up with a final answer of 1.51 times 10 to the 23rd. Now, this is our final answer. One of the things that also has to be there, make sure you always include your units. As one teacher would say, no naked numbers. We cannot do naked numbers here. Okay, now, what about if I have to do two-step calculations? And again, it seems like we're going fast. Don't worry, we have plenty of practice we can go through. Now, if I'm going through two-step calculations, notice what's flashing on the screen. Everything must go through moles. Every calculation that we do is going to go through moles. And so far, we've talked about two. We've talked about how to convert from grams to moles and from moles to particles, and vice versa. So we're going to go ahead and look at an example of a two-step calculation. Now, since 6.02 times 10 to the 23rd particles equals 1 mole, and 1 mole equals a molar mass in grams, we can use these to go directly from one to the next. Now, the question is, how many formula units are there in 25 grams of calcium oxide? If I'm using my same information, sneak peek. Now, if I'm using my same information, I know that I have 25 grams of calcium oxide. I need to find my molar mass for calcium oxide. Well, considering what I have here, I have 1 mole of calcium, which we know has a mass of 40.08, plus 1 mole of oxygen, which has a mass of 16. So my molar mass is actually going to be here. It's going to be 56.08 grams per mole. All right, now we need to put this all together because I need to go from grams all the way to formula units. So I'm going to take my 25 grams CaO. Now, since I have grams of calcium oxide here, that means I need to put my 56.08 grams, here, and my 1 mole goes up top. Now, this answer, if I stop here, gets me to moles, but I need to go one step beyond. So, my next thing is I need to bring moles down, so I'll be able to cancel it out, and I have 6.02 times 10 to the 23rd particles. Now, using this information, I can make sure my units cancel. My grams calcium oxide cancel here. My moles cancel here. I'll be left with the unit that I need, formula units. So now all it is a matter of multiplying and dividing. 25 divided by 56.08 times 6.02 times 10 to the 23rd. Take a moment and go ahead and erase this ink. And I get a final answer of 2.59 times 10 to the 23rd formula units. So I can then take this information and as we get further into stoichiometry, see how this is going to affect my overall reaction rate, depending on how much of the material is there. This is where we're going to end it for right now, and I want you to go ahead and take some time, look back over, rewind, and write down your questions. Not a lot of people are asking questions. Make sure you're asking your questions. If something doesn't make sense, make it clear. I'll talk to you tomorrow in class, and have a wonderful day.